Aloha. So for this problem, we're asked to find the diameter of a steel needle that's resting just on the surface of water, supported by the surface tension. So I've tried to draw a picture of this. I think it came out pretty well, actually. So you have this steel needle resting in the water. And this is like a little cross-section view of what's happening. So we see that the water's kind of surrounding this needle, and the tension force is what's holding it upward. And I'm ignoring the buoyant force. So just using the actual weight, mg, here in this free body diagram, since the buoyant force will be minimal, we're neglecting that. And we know that this needle is made of steel. So this is what we have going on. A steel needle on the water's surface. And from this free body diagram, since this is resting, we know that the force is balanced. So the gravitational force is equal to 2 times this force from the surface tension. And I'll also write down what we want to find, which is diameter d of the needle. So this force is from the surface tension. And the surface tension, in general, gamma is the force per unit length. And the length of this needle here is what I labeled this lowercase l. And we don't know, g is a constant of nature. We don't know the mass of this needle. That's not something given to us. But since we want to find the diameter of the needle anyway, it makes us start thinking about the geometry of the needle. So we need, so we can use the formula for density being a mass per unit volume, and we can sub in that the mass is really the density of the steel times the volume of the steel. So just putting that into this equation, and we can get the volume of the steel in terms of this diameter d that we want to solve for. And row steel, this is in chapter 10. You can find this in the textbook. And this surface tension, this is the surface tension of water. And that's also a constant that you can find in the textbook as well. So we can just keep subbing in we can just leave row steel as a constant. The volume will be this length L times the area of the needle, which will be a circle. So that's pi r squared, but r is d over 2. And we can cancel out the length on both sides of the equation, which is good because that's not a given quantity. And then we can basically just flip this equation around and solve for d. So we have just doing some things in my head here. We have, I forgot to write do from this line here. So 2 gamma divided by g and divided by rho steel, the density of steel, and divided by pi, all to the 1/2. So we have to take the square root, and then I'm multiplying by 2. So that's just some algebra to isolate d. And we can rewrite this just squaring the 2 here, multiplying by the 2 in the square root. We have this as 8 times gamma. And this is the gamma of water. That's what's creating the surface tension. So that's something we can look up in the textbook. So this is the formula we're going to use, and you can find in Table 4 in chapter 10, you can find that the surface tension of water at a sort of room temperature is 0.72 newtons per meter. And then from table 10.1, we have the density of steel, 7.8 times 10 to the 3 kilograms per meter cubed. So then plugging all this in together, we can get our final answer for the diameter. Using 9.8 meters per second squared for G. So you can plug this into a calculator and you should get about 1.5 times 10 to the minus 3 meters, which is 1.5 millimeters for the diameter of this needle.